Okay, hello everybody. So, as I said, my name is Peter Omvlee, and I'm the founder of Sketch, and I'm going to talk here about how we indeed rewrote our model like one step at a time. So this is going to be a little bit of a trip down in history, like today and yesterday. We've mostly been talking about the future, Swift, and everything else around it. This talk will contain no Swift code. Who here, I have a hard time seeing the audience, but who here has ever written any manual retain release fonts? Okay, very good. Who here has been writing Objective-C before there was the add property syntax? Okay, fewer still. Okay, good. So yeah, as they say, like those who don't learn from history are doomed to repeat it. So here I am to talk about that. So very briefly, Sketch is an application for the designers to make user interfaces like icons, websites, apps, those kind of things. And as the name already indicates, it was supposed to be a very simple application, just like if you throw a few layers on screen and that was it. So it was in 2007. I had just started at university, so I didn't really know what I was doing yet, like writing a proper application. And the first few versions didn't go anywhere really. So yeah, simple app, very simple ideas behind it. So we had a basic model view controller. The model was not using CoreData. I do sense a lot of hate against CoreData. I'm not sure where that comes from, but we did not use CoreData because we had some big fundamental problem with it. It was just because it didn't exist yet. So the model was basically a tree of NSObject subclasses, and so you would implement NS coding, and basically on saving and loading you would just run through the tree and save every object to NS keyed archiver and then down to disk. Drawing was basically just an NS view subclass. You override draw rect. Every layer knows how to draw itself, and just recursively the document draws itself. So a very simple model for a very simple app. But then we started to become popular in around 2012, 2013, and the model of the application that had been architected for maybe a couple hundred layers at most, suddenly we were dealing with like trees of more than 100,000 model objects, and then these simple assumptions that I made years back started to completely fall down. And so yeah, we are in a bit of a problem because the entire model is a bit of a mess. Like it started really, really simple. I have basically a layer class and a style class. Those were written by hand, and that's fine if you just have two layers and you have no big plans. But bit by bit, you start to add more classes, and everything is still handwritten. And yeah, saving is slow, loading is slow, rendering is slow, undo is unpredictable. Like, how do we dig ourselves out of this mess? So that's the story of this talk. So the first thing we had to solve in order for us to solve all these other problems we were having is have some kind of like stable base. As I said, each model object was basically handwritten, encoding, decoding, copying, undo. Everything was just written by me by hand for every property. And that becomes a bit of a mess when you grow from like 2 classes to something like this in your model. This is just the hierarchy, not the relations in between. And so if you have all of this handwritten stuff and you want to make like one sweeping change across your model, you'll have to write it. You have to write it for every class, and it just doesn't work. So how do we unify the behavior between all these separate classes? It's like, can we get like one system, like one way in which every model object knows how to do a certain thing so that we can predictably make a copy of the document or predictably do undo, for example. So I started looking at key-value coding and key-value observing. Just very briefly, key-value coding is like a way you can extract, you can ask for properties of a model by string instead of having to like hard code the access. And key-value observing is a way for one class to know about either itself or another class automatically when certain properties change. So the idea was, well, I can have a base class that knows how to do all these things, and subclasses can like register key paths to do this. So the base class basically have, for example, a key paths method, which would be empty because the base class doesn't do anything. But a subclass could add key paths to this array. And then, for example, when you were archiving, you would just, in the base class, you would run over these key paths and write them down to disk. So that works. I mean, we can get fairly predictable, simple archiving and unarchiving copying code, like using basically this. Undo, we can also sort of solve using key-value observing. So the idea was that every class, or every instance of the base class would observe all properties on itself. And whenever a change was made in any of those properties, like this method would get fired. And basically you would get the old value out, the new value, you would compare them, see if the undo registration is enabled, and then just register the change in the NS undo manager. So this is a way in which you can get the same undo behavior for every property in every instance in your model. I should explain for those who don't know. Undo management is typically done using NS undo manager, and the idea is whenever you make a change to a property in your model, you record the inverse of that change to the NS undo manager, so that when at some point the user presses undo, it basically rewinds all those steps to get the model back at the state where it was. And this works, which is nice. So we had tons of custom code removed, like all the custom encoding and decoding, copying, undo. All of this stuff was now handled by one base class in a predictable way. But we have a problem. And when we're now talking, it was 10.7, I think, Lion, where Apple introduced Autosave. Because saving is really slow. If you want to archive 100,000 model objects down to disk, and you have to run them through NS, with NS coding through NS keyed archive, run them down to disk, that takes a long time. And that was sort of fine as long as like save was an action that was started by the user. They would go to file and save. Maybe your application would beach ball for a second, but then it was done and the user could continue. Not ideal, but workable. However, in 10.7, the system would just decide at random intervals, like now is a good time to save. So if you were dragging an object across the screen halfway, the system could think, well, let's start saving everything down to disk, and just halfway to drag, the entire application would freeze for a second while you were writing everything down to disk. So this is clearly not ideal, and users complained, and rightly so. So what's the solution to this? Well, Apple's advice was like to first make a copy of your data, and then serialize and write it down on a background thread. So instead of doing this, so you're just on your main thread, user presses save, you start encoding, you write it down to disk. You're supposed to do something like this. So first make a copy of your model, which is hopefully quick. Hand it off to a background thread, and while your main thread continues to receive user input, you encode and you write down to disk. So, how do you make these copies? Like, they make it sound so simple, but if you have a tree of 100,000 objects, that is still really slow if you're just going to make a full copy of that every time, especially the way we were doing it with key-value coding and key-value observing. More about that later. So we came up with a scheme, Immutable Copies, in which we would try to, so instead of handing back like real copies of the model, we would return what were enforced as immutable copies. So if you ask for a copy of a group, you would get an immutable group back. Think of it like NS mutable array versus NS array. The nice thing you can do then is like when you get asked for a copy immediately after, you can just return the very same object. It's a bit like when you ask for a copy of NS array, it just returns itself with a +1 retain count. So the way that looks in a tree, so when you ask for a copy of the root of the tree, recursively everything makes a copy, but every node in the tree holds on to the last copy that it made of itself. So, and if the document then doesn't change at all, and you ask for another copy of the root, well, it already has a pointer to that copy, so it just returns that, and you basically get an instant copy. What happens though if something changes in your model, because that happens? Let's say a user drags this group across the screen. So now we need to throw away that copy, because next time they ask for a copy, we can't be handing back an old copy. We can't modify the copy either, because it's an immutable copy. And that's very deliberate, because another thread may be in the process of saving this down to disk. So let's just pretend that copy never existed. Now we also need to tell our parents that we have changed, so that it can throw away its copy, and then we're here. Next time we're going to save to disk, and we need a copy. We ask the root of the tree for a copy, and we need to make 2 copies rather than 5 new ones. So this is like a very nice performance win, especially if you have a tree of 100,000 objects, which is very wide but not very deep. So yes, this works. And we started using it for rendering as well. So we were able to move rendering from the main thread to a background thread finally, because we now had a way to get a cheap safe copy of our thread on a background thread. The nice thing here is also that there is no locking involved, no complicated cross thread management, like what do we do with changes? No, there's just every new copy is an immutable tree, and as long as data doesn't change, there's no need to lock around it. Sketch is still slow though, even though we have moved rendering off the main thread and we no longer stall at random moments because of saving. Sketch is still slow. Turns out the KeyValue Observing is really slow. Really, really slow. Especially setting up the observations of KeyValue Observing and then tearing it down again. Well, how slow exactly? So I wrote a little sample app back then to verify my assumptions. I would make 1 million model objects. Each model object would observe 2 properties of itself in order to do the undo that I showed earlier. I would make 1 or 2 changes to those model objects and then throw them away again. So very simple. 1 million objects, make a few changes, throw them away. How long does that take? 30 seconds, which is really long, because if you do it the manual way, and just like you make 1 million objects, you override the setters instead of doing wizardry with KeyValue Observing, the exact same behavior only takes 0.2 seconds. So the overhead of KeyValue Observing is enormous. So it turned out to be a really, really bad idea that every model object in a model was observing itself for changes in every property. So yeah, how do we fix this? We don't want to go back to manually writing all the code in all of our classes, but we can't deal with the runtime overhead of KeyValue coding, KeyValue Observing. So, as has come up a few times already this conference, we started looking at code generation. Like, can we write out all this stuff at compile time rather than incur the runtime overhead? So we use a simple template engine to write our model objects. How do we define our model? Well, we can use the CoreData model editor because it comes with Xcode. Sorry. So I was assuming like everybody knows new CoreData, but I assume maybe that's not the case. But there used to be this popular open source companion to CoreData the mode generator, which would basically, there was before, I think, CoreData like actually had proper properties on its objects, but basically it would read out a CoreData model editor and create like your classes for you, like one underscore prefixed one for the auto-generated stuff, and one which you could in which you could put your own code. So we did this as well. So that we added our model information to the CoreData model editor. We wrote templates, and then basically we had our own model, which was almost but not quite like CoreData, like as it was said in the first talk. Like if you don't use CoreData, you end up reinventing CoreData. This is what happened in a way. So the templates would look like something like you see here above, like just as again simple encoding. Here's a loop, sort of, and for every property you just write out encode with encoded object or encoded integer for the name for a key, and what it outputs is the stuff below. So this is basically as fast as you could write it by hand, but yet it's nicely generic behavior for every object, every property in your class. In the same way, this is how undo then is done. Like don't try to understand what happens, but you can see sort of on the left, you can see by the indentation there are a few sort of if statements. Like if it's an object, do this. If it's like an integer or a float, like take a shortcut. And what you get all on the right is a nice optimized way of doing undo, which works. It's a lot faster. It really is a lot faster. We open source this, like turning CoreData via templates into your own stuff. The name Coma was supposed to be a witty abbreviation of something that we've long since forgotten. So, yeah, I don't know. But it is open source, not very well documented. But if you want to go there, be my guest. So we're in much better shape now. Our model is predictable, it's fast, we can do multi-threaded things. What's next? Well, how far am I? Yeah, I'm fine. We have a little bit of a problem still with undo. So as I've explained earlier, NS undo manager, you throw undo invocations in there, which are the reverse of every individual change in your model. And that's really brittle. Like NS undo manager is this black box, you throw stuff in and you hope that it comes out in the right order with exactly the right properties. And very often that does not happen. When it happens, it's way too late to find out like what actually went wrong. Because like, you've been throwing undo invocations in there for a while, and then a few minutes later the user actually does an undo a few steps back. And if you haven't like retraced your steps exactly, NS undo manager just gets confused. It says either like it references something that is no longer in memory, or just it messes up. Something goes wrong in its internal state and says, well, sorry, you've lost undo, you've lost all your undo history. I can't help you. And the problem is when that happens, like the sequence that went into it has long since been forgotten, and you don't really have a way to find out like what went wrong, or like which command did you put in there that screwed things up. So can we do undo in sort of a simpler, better, more predictable way? And so we started thinking, like first try to patch like points where it might go wrong, but it was never really satisfactory. So we started looking again at our model. Remember, we have a model, we make copies of it, and then we write those copies down to disk. So in a way, these immutable copies of a model are like snapshots of the state of a model at a certain point in time. Can we just think of undo as basically an array of those snapshots, right? So every state of a model, every undo state is just a tree. And when I want to go back in history, I just get an old tree and give that back to the document. And this should be much simpler conceptually than like being here and then having to replay our steps in order to get there and hope we get there in one piece. Here it is just an NS array of trees. Seems like a very nice idea, and in fact, we can sort of already build this because, well, we have a way of creating these trees. We've been doing that for quite a while, for saving and rendering. We have a way of turning those immutable trees back into a proper document, because that's what we've been doing when we load up from disk. So all the pieces are there, basically. So can we do that? Turns out we can. Although there is one thing that you might think of, like, well, wait a minute, not so fast. Does this not take up way too much data in memory? It's like I was talking about a tree of 100,000 objects or more. If you have an undo history of a few hundred steps, like multiply those numbers, and doesn't that take up way too much memory? Well, in fact, not necessarily. Because as we saw earlier, like if I change the group, I would throw away its copy, and so up to the root. So if I make two subsequent trees after these edits, what I end up actually are two trees that share most of the objects. And since between every undo state you never change every object in the entire model, there's only ever like 1 or 2 or 3 objects plus a call to the root. Most of these trees actually share the same objects. So memory usage is not really an issue, and we can just do this, right? We have an array of trees which actually share most of the objects. This is what we did. It works really well. We were able to get rid of so much custom, like NS undo invocation hacks. So as you saw, we had to override every setter in our model to get it to generate these undo invocations, plus redo invocations, and work out like that they are not exactly the same. There was so much complication around undo, so much black wizardry that never really worked. Like what we now have is a really simple model, right? It's just an array of trees. It's very simple. It can't really break, which, of course, they take that with a grain of salt, but like there are only 2 basic components to it. Like one, make a tree and put it in an array. It's easy, because we know we can do that already. And restore a tree. We know we can do that already as well. And what is also really nice, it basically have constant time undo. It's like if you want to go to the previous state in my array, it's like, well, here's a tree. You hand it off to the document to display it, and you're done. If you want to go all the way back to the first state of your document, it's still just a tree that you hand to the document, and you are done. Whereas with NS undo manage, you had to replay all those actions, so that if you want to go back 1 step, you might be playing back 100 actions. If you want to go back 3 steps, you might be playing back like 300 actions, and all the changes that cascade through your model as a result of that. With this, you don't have any of that. It's just a tree. There is one minor performance problem with this, which is, like as I showed earlier, like we have this real tree, and then we create these immutable copies from this. So the real data is in that real tree. Like when we load from disk, we load the immutable copies, and then we turn it into a real tree again. So when you restore from undo, we take an immutable tree, and we have to turn it into a real tree of data. So that would be like initializing another 100,000 objects if your document is really big, and that just takes a while. Well, how can we not create this entire tree every time? Well, we take a lesson from CoreData, and we do faulting. So basically, after undo, we only create the first node of the real tree, and then we are done. It's faulted, but as soon as some other part of the application needs something down the tree, the page will actually check the immutable copy that it still has and say, well, I actually have 2 children which are now being called for, so I will create those right now. So the rest of the application doesn't need to know that most of the tree is never actually created. And this is one of those moments like you say, wait a minute, what just happened here? Because we started with like a real tree, and just we created throwaway copies of that, and so it was clear that the truth was in those real trees that lived on the main thread. But now we no longer have all of those copies on the main thread in memory, and the tree is very incomplete, as you saw, right? And now the truth lives in these immutable trees, which are the real thing, and like what used to be the real tree is now just a convenient editable proxy for the rest of the application, because it's just a bit hard to deal with immutable trees. And so we've basically just flipped the entire architecture of the application around. And we now have a much simpler model, a much simpler concept of the entire application. We have a very pure model now. Like our model is a tree, a value tree with basically immutable objects. Our history is just an array of trees. And every change in the model is basically a change from one tree to another tree. And when you think about it in terms like that, you have a very you can do all sorts of interesting things. Like what if your model is completely mutable? What you might have to do is like have complicated ways to track changes between edits. Like for example, you need to redraw part of the view, so you need to know exactly which properties changed on which objects in order to tell the view like, hey, this is what you need to redraw. You no longer need to do all of this complicated stuff. You just have a tree. You go from one tree to another tree. You basically do a diff, and you find out what has changed. So this simplifies life on many fronts. And yeah, in all, going back to the beginning of this talk, like as we started out with this very traditional design, which basically broke down under us, and one step at a time, we've completely flipped our model on its head, and now we actually have a really nice thing. And we didn't go back to our cave and rewrote the application, losing all momentum that we might have had in the process. No, one step at a time, you can really turn your application around. So resist that big rewrite, and trees are awesome. So thank you.
Thank you. Thank you.
So I really like the last part where you had your mind blown away. It's really pragmatic. Like those days with Swift were really encouraged to use immutable, and sometimes you don't always know exactly why. But in this case, you had a really pragmatic and really concrete example of here is what's gonna bring to us, and that was really interesting to see that.
Thanks.
And speaking of Swift. How do you start adding Swift and switching to Swift with a Sketch, which is probably a huge code base?
Yeah, at the moment, all the code base is still in Objective-C. We've only started writing some tests in Swift because every year we keep finding a reason why we can't start using Swift yet. Like at the moment, so we have a lot of static libraries in our app, and those don't yet work with Swift. Well, it's supposed to work now in Xcode 9, but Xcode 9 doesn't run on 10.11, which we still support. Oh, yeah. And so we have Mac Minis running our tests. Some of those still on 10.11, and they need a version of Xcode to run. So we have to wait until we drop 10.11, and then maybe yet another hurdle will present itself.
Yeah, and do you see some interesting features that could help you in the development of Sketch in Swift?
In Swift, yeah. Well, the idea of immutability and all its benefits has really been made clear to us over the past year. So yeah, that is an aspect that is nicely. So if you can nicely encode that in the language, I imagine it has many upsides.
I can see that.
So I of course, Sketch is quite a complex application. There is a huge code base. How do you manage to ship changes while still keeping the application working. I mean, without breaking anything, basically.
Yeah, as I said, like one step at a time, like really small changes, like it's really small changes, and try to plan it such that you can ship those. It's like at some point, our immutable copies were not really separate immutable copies. They were just copies of the real thing with the runtime flag. Like, well, don't set up any KeyValue coding, KeyValue observing things, because that was like one small step we could take, and then we knew the next step was turning those into real objects.
Yeah, and with this approach, isn't it kind of hard to test, to actually write tests for that? It seems that it's kind of complex code that could lead to a lot of corner cases. Did you write a lot of tests to exercise that?
Specifically these transformations?
Yeah.
Yeah, well, we try, but yeah, there's so much legacy code which wasn't tested. Like, I mean, that's another whole area where I could go into. Like, everything used to live in the main target. We didn't have any static libraries, so when you wanted to test something, your only choice was basically to first launch
everything.
Just to launch the app to be able to test anything. So there are many small steps, and there's a very long story I could tell about all the small things, but I only had half an hour. So.
Sure. Do you try to do A/B testing on some users, or just everything is shipped at once?
No, we're fairly opinionated ourselves on how we think stuff should work. Of course, we do ask users.
Apple
like,
style.
Yeah, no, we do talk with users about what they want, but yeah, it's first and foremost where we think we should take the app.
And about performance, are you waiting for user to complain, or do you yourself decide that, oh, that part of the app is not fluid enough, then we're going to optimize that? Do you have some metrics? How do you decide when you start to actually spend time optimizing? And maybe also, when do you stop? Because as developers, we all know that at some point you want to optimize and optimize and optimize, and you spend a lot of time optimizing and re-optimizing things that are maybe not really necessary.
Yeah, so there are a couple aspects to that. Like, our rendering performance would be nice if it was always faster, because it's still like our rendering is basically built on top of core graphics, which is mostly CPU bound, and those don't get much faster, so you have to sort of juggle with the resources you have. Wow. So you always try to do the best you can there, but there are also like often hidden edge cases somewhere deep in the model, and you only find those really when a user comes to you like, well, when I do this and this in this particular document, then it turns out to be slow, and then you can take active steps to look at it. Like, just like, yeah, you try not to write code that is slow, but like in such a big model, you can't just like just go in and say, well, today I'm just going to look at performance, because you don't know where to look.
So if I have problems with performance on Sketch, I can send you my files, and you're going to optimize that? Of course.
Like, for example, there's one complex area, the shapes and the Boolean operations. There's a lot of mathematical complexity in there with nested while loops, and like sometimes in some edge case you don't actually get out of that while loop, because like, well, shapes and vectors and floating points, and it's just really hard. So in those cases, especially, like, we need a sample to solve it, because like otherwise, where do you start?
A question which is related to that, and since you were speaking about undoing, if you can undo some choices about your what you did in the code base of Sketch, what would that be?
Like removing features? Wow.
No, I wouldn't. We should have started to look at the code generation immediately, rather than try to take a shortcut through KeyValue coding, KeyValue observing. Like, that is the one big thing, like, which we shouldn't have done. There are more, but that's the first.
Without having done it, you maybe wouldn't be aware that it's not the right path.
No, indeed.
Sometimes you have to make those mistakes.
Yeah. And that's also like the decision was made when we did not have that many users. The documents were not that big yet. You think, well, I think we can do it. But then the documents grow bigger and bigger, and then now we can't really.
And users are starting to do things that you were not.
Indeed, yeah.
Do you have like other apps that you develop that are used as sandboxes or test benches of some of the ideas that you described here?
No, we just we just have Sketch.
Okay.
To put everything. Okay. thank you very much
Yes.
for this talk. It was
Thank you.
really interesting.
Yeah.
Thank you.
Yeah, so
let's see. Thank you very much.